Hello everyone, my name is Saurabh Kumar and I am going to present my paper DeepDetect, a practical on-device Android malware detector. The growth of Android malware is increasing rapidly. A report published by GData shows that in the year 2019, around 4.18 million new Android malware has been discovered. With this rapid growth, a malware may get unleashed into a mobile device by bypassing the defense system of Play Store or through a third party market and sideloading. Hence, on device malware detection is required. With this observation, our goal is to design an on device malware detector that is faster, consume less device energy, provide high malware detection rate with low false alarms. However, the main challenge in designing such a system is the limited energy of a mobile device. Let's look into the design of DeepDetect. It has three phases: feature extraction, feature engineering, and building the system. Let's look into the feature extraction. We extract features from two sources, manifest file and DEX code. We use all features from the manifest file, but from DEX code, we extract only opcode sequences by using dexlib2 library and operates in memory. Now, let's see the feature engineering process. It has three major components: feature selection and encoding, category wise feature reduction, and last, feature reduction on the combined feature set. Let's look the feature selection and encoding. We encode features either based on their count or its presence. We take count of all user defined components such as activities along with the n-gram opcode sequences, whereas all system defined entities like permissions, we use them as binary features. These are the features which we extract from an APK. Original and encoding shows the count of features before and after the encoding phase, respectively. Let's look into the category wise feature reduction process. It has two subcomponents: reduction based on correlation and optimal feature identification. In correlation based reduction, we use Pearson correlation, which lies between -1 to +1, where 0 denotes the weak correlation and +-1 represents strong positive and negative correlation. Therefore, we observe effect of different correlation values on feature set size versus accuracy and select 0.8 for permissions and hardware components, whereas 0.9 for 2 gram opcode sequences. These reduced features are then used for optimal feature identification. In optimal feature identification, we use RFECB with random forest as classifier and accuracy as ranking function. As a result, RFECB provides a grid of score with optimal number of features that achieves highest accuracy. However, if we carefully observe number of features versus accuracy graph, we see that with a significant less number of features results in an accuracy closer to the maximum achievable accuracy. With this observation, we define a threshold RFET, which is a penalty in choosing less number of features in terms of accuracy. Hence, we evaluate features performance with different values of RFET and observe a drastic reduction in feature set size for 0.5 as RFET threshold. These category-wise optimal features along with the numeric features are then used for combined feature reduction phase. This step comprises of two subtasks. First, combining all features and selecting best combination, and second, reduction in combined feature set. First, we combine all features and observe the result for all combinations. and found two different combinations with highest accuracy. First, a combination of requested permissions and opcode sequences, and second, the combination of numeric features, permissions, and opcode sequences. We select the second combination because the contribution of numeric features is significant when combined with permissions. In combined feature set reduction, we eliminate features that requires extra support. Such features are intents and custom permissions. We observe effect either removing one or both, and finally removes intents as it does not impact model performance. This final feature set is then used to design DeepDetect. For more details about the feature engineering process, please refer to our paper. Now, we will see the steps to build DeepDetect. First, we extract features from the dataset. The extracted features are then passed to feature engineering process to obtain relevant features, followed by the learning model. All these steps are performed on a server machine. Final model is then zipped into an APK to detect malware on a real device. We have already seen the feature extraction and feature engineering processes. Now we focus on the learning final model. For final model, we use random forest classifier, why random forest, and why not other classifiers like SBM, KNN, or neural network. The reason is it is an ensemble method. It works based on the information gained and does not require feature scaling. For example, see the result using multiple classifier with and without feature scaling and observe that the performance of random forest model is not impacted because of multi-scaled values. We use TensorFlow library to learn final model and convert it into a TensorFlow Lite model for on-device detection. Let's see the on-device detection process. Whenever an app gets installed or seek an update, we generate a feature vector. This vector is then passed to detection model for the results, that is either benign or malware. If it is a malware, we notify to the user and give an option to uninstall the app. This is the process of designing DeepDetect. Now we look at the performance of it. To measure the performance of DeepDetect, we use following metrics. To measure runtime performance, we observe execution time and device energy consumption. For evaluation, we require a dataset with ground truth values. Hence, we collect multiple datasets. For training or known sample, we randomly select 80% samples from AMD, Virus Air, and Play Store datasets, and remaining 20% as evaluation set or unseen sample. For the new samples, we download samples from Windows Zoo for the year 2019 and also use Pegasus samples for evaluation. For obfuscated samples, we obfuscate malware of Android Zoo 2019. First, we see which feature is best that can be extracted from DEX code efficiently. Hence, we extract 7 different features from DEX code and trained a random forest classifier on training set. We evaluate model against the evaluation set and obtain ROC curve and AUC values. As a result, we found three feature sets 2 gram, 3 gram, and USR, which provides more than 99% of AUC score. However, the size of USR is relatively large as compared to 2 gram and 3 gram. Next, we see the runtime performance in extracting these features. For runtime efficiency, we use 5 different apps. We extract features on 3 different smartphones and measures execution time for each application and average execution time on each device. We observe that 2 gram takes approx 5.32 seconds on the OnePlus 7 Pro, which is 2.13x and 2.53x faster than restricted APIs and sensitive APIs respectively, with 6.06 seconds of overall average execution time on all devices. When we measure device battery consumption, 2 gram consumes 0.45% battery on the OnePlus 7 Pro, which improves device energy by more than 2.1x compared to non-op-code based features. However, average energy consumption across all devices for 2 gram is 0.7%. This battery consumption is obtained by analyzing 50 apps. Now, we look robustness of DeepDetect against unseen and new samples. The model is evaluated against known, unseen, and new samples. We observe precision, recall, F1 score, and FPR along with the ROC curve and AUC value. Evaluation shows that DeepDetect can detect more than 97% new malware with 1.73% of false alarms. We also evaluate DeepDetect against 5 samples of Pegasus malware. Interestingly, DeepDetect is able to detect all samples of Pegasus. Next, we look resilience of DeepDetect against obfuscated malware. We create a new obfuscated malware dataset by obfuscating Endozu 2019 malware. To obfuscate, we use OffusFEK tool and obtained 4993 unique samples, which lies in 6 categories. We evaluate DeepDetect on same samples, that is non-obfuscated and obfuscated, and observe the drop in the detection rate. We do not observe any drop under the category of trivial and renaming. However, we see a maximum drop of 2.47% for the code obfuscation category. The overall average detection rate against obfuscated samples is 95.57%, which is a drop of 1.55%. For more experiments and results, please refer to our paper and a web link provided in it. Unlike other systems, our solution is also having some limitations. It cannot detect malware whose malicious behavior is present only in native code. It cannot analyze packed malware whose entire code is encrypted except for unpacking logic. It cannot detect malware that downloads malicious code from external sources. In conclusion, with an effective feature engineering framework, we have designed DeepDetect. We found that DeepDetect can detect more than 97% new malware with a false positive rate of 1.73%. Furthermore, DeepDetect can detect 95.57% of obfuscated malware. Lastly, DeepDetect can analyze an app in approx 5.32 seconds and consume 0.45% of total device battery to analyze 50 apps. Thank you.